All right, let's go ahead and get started. I want to welcome you now to Unit 5. This is chemical bonding. This is going to be a very important unit because of the fact that we spent Unit 4 surveying the periodic table. We said that, well, there are over 100 elements in the universe. These elements don't occur in isolation. They are bonded to each other for the most part. So what causes atoms to bond to one another? Well, chemical bonds form because atoms are trying to feel as though they have a special number of electrons around them, and that number is 8. So all atoms are trying to achieve the octet. They're trying to get 8 electrons around them, and that is really what drives chemical bonding and how elements or atoms bond to one another. The outer shell or valence electrons are the ones that are involved in chemical bonding. And remember we said when we were studying the periodic table that elements in the first column, we call those the alkali metals, have 1 valence electrons. In the second column, 2 valence electrons, and so on. So the type of bonding which occurs really depends upon the difference in electronegativities between the atoms that are involved. The difference in electronegativities. Remember that electronegativity increases as you move left to right across the periodic table and from bottom to top, right? So fluorine, we said, had the highest electronegativity of all, and I want you to remember its electronegativity. It has an electronegativity of 4.0. So fluorine is going to be right here on the periodic table, and it's going to have the highest periodic table, the highest electronegativity of all, with a electronegativity of 4.0. There are no units. So we'll remember that that's the maximum electronegativity that you can have. Now, bonds between metals and non-metals, that is, elements from the left side of the periodic table and the right side of the periodic table, are ionic. So if you have something from the left, say sodium, for example, and something from the right, say chlorine, for example, sodium and chlorine are going to form an ionic bond. Bonds between two nonmetals are generally covalent. So if you have two things from the right side of the periodic table, those are covalent bonds. And bonds between two metals are metallic bonds. So again, remember that if you've got something from over here and you've got something from over here, that's a metal and a non-metal, they're going to form an ionic bond. An ionic bond. But if I have two things from the right-hand side, two non-metals from the right-hand side of the zigzag line, that's going to form a covalent bond. If I have two things from or two or more elements from the left of the zigzag line over here in the metal area, then I'm going to have what's called a metallic bond. So I've got ionic, covalent, and now metallic. So we want to discuss these individually and talk a little bit about how they're formed. Let's start with ionic bonding. Ionic bonding is a type of bonding in which chemical bonding results from the electron or electrical attraction between large numbers of cations and anions called ionic bonding. In purely ionic bonding, atoms give up their electrons to other atoms. So if we have, for example, I've used the example just a moment ago of sodium and chlorine, sodium is going to have a tendency to want to lose an electron. That's true because of the fact that it's on the left side of the zigzag line, and elements to the left of the zigzag line are going to want to lose an electron. If it's an alkali metal in that first column, they're going to want to lose 1 electron. So here's sodium. Here's the structure for sodium. Sodium comes in contact at some point in the universe with a chlorine atom, and chlorine desperately wants to gain an electron because it's one away from the next noble gas. So sodium and chlorine make a deal. Sodium loses an electron. That electron is transferred to chlorine so that we get 2 ions, a sodium ion and a chloride ion. Sodium ion, that's a cation, and a chlorine atom, or chloride ion, that's an anion. Now remember that in ionic bonding, valence electrons are transferred from one atom to the other. They're transferred from one atom to the others. We'll see later in covalent bonding there's a sharing of electrons, But we're talking about an ionic bond in which there is a transfer of electrons. Now, in ionic bonding, this is going to happen many, many, many times. And I'm showing this here in this diagram so that even though we see that sodium will transfer one electron to one chloride ion, that happens many, many, many times to form something called a crystal lattice. So unlike in covalent bonding that we'll look at one time where it happens individually, a covalent bond is a single event. An ionic bond means that there are many, many, many transfers of electrons from positively charged cations to negatively charged anions, okay? All right, let's switch our attention now to covalent bonding since we know a little bit about ionic bonding. So in covalent bonding, as the name implies, there's a sharing of electrons. Covalent bonds result from the sharing of electron pairs between two atoms. So let's in this case take these two atoms here. So this one atom, right? One atom is sharing an electron with another atom. And here's the sharing part right here. These are the shared electrons between these two atoms. So note covalently bonded atoms are sometimes called molecular compounds. Molecular compounds. Now, if the electrons are shared equally, the covalent bond is known as a non-polar covalent bond. A non-polar covalent bond. So on the left side of this diagram, I have a certain number of electrons, and let me count them up for you. 1, 2, 3, 4, 5, 6, 7. 7 electrons in the outer shell of the atom on the left. Now you may say, well, what about the atom what about the other electron? Well, that's coming from this atom. Let me change pen color so you can see it just a little bit more clearly. I'm going to start here with 1, 2, 3, 4, 5, 6, 7 valence electrons in the second atom, right? But notice that both atoms now feel as though they have 8 electrons. Even the atom on the left, even though it has 7 electrons coming from its own valence pool, it feels as though it has an 8th. So it feels as though it has 1, 2, 3, 4, 5, 6, 7, 8. And this atom feels as though it has 1, 2, 3, 4, 5, 6, 7, 8 as well. So that's what we mean by covalent bonding. Covalent bonding is a sharing of electrons between atoms like we've seen here. All right, now let's make a little note. Ionically bonded atoms have a higher melting point than covalently bonded atoms because the atoms are much more tightly bonded together. So if you have something that's ionic, it's going to have a higher melting and boiling point for that matter than something that's covalent because of that greater attractive force of the ionic bonds. Now, if the electrons are shared but one atom is significantly more electronegative than the other, but not so significantly that a bond is ionic, then the bond is polar covalent. Now let's look again up here at this sharing situation. On the left-hand side, we have an atom that had 7 valence electrons. On the right, we had an atom that had 7 valence electrons, right? And so there was an equal sharing of electrons, right? There's an equal sharing of electrons between these two. Whatever this atom was, is this atom exactly, right? Now, let's compare that to this situation, however. In this situation, there is a sharing of electrons, but it's an unequal sharing of electrons, right? It's an unequal sharing of electrons, with the atom on the right-hand side having more control over the electrons in the sharing than the atom on the right-hand side, thus the bigger cloud. So on this right-hand side, there's a bigger cloud than on the left-hand side. We call this greater electronegativity an electronegative situation. So this atom is more electronegative than the atom on the left-hand side, right? So this symbol right here is the symbol for electronegativity. Let me write that for you. It looks something like that. So electronegative, just like that. Okay? And electropositive is going to look like that, right? So there you have it. So we've got ionic bonding, where there is not a sharing of electrons at all, right? There's no sharing whatsoever. Then we've got covalent bonding, of which we can have equal sharing. We call that completely nonpolar covalent. And now we're looking at a situation here where we have polar covalent. Polar means that there's one side that is more electronegative than the other. In the Earth, for example, there's two different sides to the Earth, or two different poles on the Earth. There's a North Pole and there's a South Pole, right? There's a North Pole and there's a South Pole. On a magnet, there's a positive end and there's a negative end. Now, let's contrast it. So that's a polar situation, by the way, with a magnet. So let's contrast this with the ionic bond cloud, which you recall looked like this. All right? So notice that there is no sharing of electrons in an ionic bond like the one shown to the right. So this would be an ionic bond situation, right? Where there's no sharing. One electron, or one atom, I should say, completely took over the other. So this one on this side might have been, chlorine, and this one might have been sodium, right? So sodium gave up an electron to chlorine. So an electron went from here to here. That was a transfer, so that's called an ionic bond, right? That's called an ionic bond. Let's move on. Metallic bonds. Now, metallic bonds are bonds formed between atoms which are both on the left side of the periodic table. There can be more than two. Now, these are called the metals, and metals are characterized as being malleable, ductile, and lustrous. If you see, for example, a copper pot is, in the kitchen, is one that is shiny, right? That means lustrous. It can be hammered into various shapes, right? It can be hammered into the shape of a pot, and it's malleable. It's bendable, doesn't break. Now, metals are also good conductors of electricity because of what's called the sea of electrons. And I want you to remember that phrase, sea of electrons. Well, here's what it means. It means that electrons are free to move anywhere in the metal that they desire. All right? This allows electrons to move very freely around the metal atoms. Now, metals have a very high melting point. That's because of the attractiveness. But I want you to notice here that the electrons in metals are not bound to any particular element, right? So these electrons are free to move anywhere they want, right? They can move anywhere. And thus we use the name sea of electrons, right? The reason that electricity works through a, say, copper wire is because copper is a metal. And copper allows these electrons to travel anywhere they want, right? Anywhere they want. So we call that situation the sea of electrons. So again, the sea of electrons makes metals very, very good conductors of electricity. All right. The melting points of metals are even higher than ionic compounds, right? So let's talk a little bit about melting points again. The melting point of covalent compounds is lower than the melting, where we have sharing of electrons, lower than the melting point of ionic, and those are lower than the melting point of covalent, of metallic, okay? So it's, once again, covalent, followed by ionic, followed by metallic, just like that. Folks, we're going to ask a few questions on the next one, but I think that'll do it for this one. I'll see you in the next screencast. Thanks.